Have you ever felt that when using AI assistants like ChatGPT, sometimes you have to wait quite a while to get a response? This is because when large language models process our questions, they need to perform massive amounts of computation. Today, let's learn about an innovative technology from NVIDIA called FFN Fusion. With this technology, while maintaining the model's performance, researchers successfully improved response speed by about 70% and reduced operating costs to approximately 1/35th of the original. Let's use a simple analogy to understand the current issues faced by large language models. Imagine the model's computational process as a very long production line, where each computational layer must wait for the previous station to finish its work before starting its own task. In traditional large language models, the attention layer, attention, and the feed-forward network layer, FFN, are like different stations on this production line, and they must work sequentially in a fixed order. When the model becomes increasingly large, reaching hundreds of billions of parameters, this one after another working method leads to significant waiting time. How did the researchers solve this problem? They proposed a two-step solution. First, they discovered that in the model, some checkpoints, attention layers, could actually be safely removed. Just like on a busy highway, not every toll booth is necessary. Through careful analysis, they identified the attention layers that could be removed while ensuring that this removal would not affect the model's performance. The second step is even more interesting. Imagine if we merge several consecutive workstations on the production line into one large workstation, allowing multiple tasks to be performed simultaneously. What would happen? Researchers found that after removing some attention layers, the correlation between certain consecutive FFN layers was not strong, and they could work simultaneously without issues. To better understand this process, let's look at a specific example. Originally, the path of information transmission in the model was like this: FFN1, checkpoint, FFN2, checkpoint, FFN3, checkpoint, FFN4, just like passing through multiple toll booths on a road. After applying FFN fusion, the path becomes FFN1, checkpoint, FFN2, FFN3, FFN4, working simultaneously, checkpoint. This not only reduces the number of pauses, but more importantly allows multiple workstations to process tasks simultaneously. During this optimization process, the researchers also discovered an interesting phenomenon. Different FFN layers have varying demands for computational resources. Just like in a factory, some workstations require larger operating spaces, while others can be smaller. Based on this discovery, they designed different workstation sizes, layer widths, for different layers during model training. In the Ultra 253B base model, the FFN widths of different layers are reflected through scaling multipliers. This means some layers were set to narrower widths, about half of the original, 0.4875 times, while other layers were set to wider widths, nearly 5 times the original, 4.875 times. These widths were determined after training completion and remain fixed during inference rather than being dynamically adjusted. This is similar to urban road construction, where road widths are pre-planned based on traffic flow analysis. The widths are fixed after training and do not change dynamically during inference. How effective is this optimization method? The research team chose a large model for testing Llama 3.1-405B instruct. Test data shows that the optimized model showed significant improvements in two key metrics. Response speed increased by approximately 1.71 times. The cost per token, text unit, was reduced to 1/35th of the original. To put it in more intuitive numbers, if it originally took 1 second to process a token, now it only takes about 0.58 seconds. If the original cost was $1, now it only costs about $0.029. It's worth noting that these improvements did not affect the model's performance. The researchers also discovered an interesting phenomenon. This optimization method appears to be particularly suitable for large models. They conducted tests on models of different scales ranging from 49B to 253B parameters. The results show that the larger the model scale, the more pronounced the optimization effect. This finding is important because it means this technology may potentially assist in the development of even larger scale models in the future. However, like any AI technology, FFN Fusion also faces some specific challenges. Some early layers in the model have a significant impact on many subsequent layers, which limits their potential for parallel processing. When dealing with smaller batches of data, optimization effectiveness may be affected. Additionally, the complexity of technical implementation cannot be overlooked, requiring careful analysis of the relationships between layers to ensure that optimization does not compromise model performance. Overall, this technology is still in the research stage, but it has already demonstrated some unique advantages. For example, it can be used in combination with other optimization methods, such as quantization and pruning. In some cases, researchers have even found that complete computation blocks containing attention layers can be processed in parallel, which provides new insights for future model design.